Hello, my name is John Dowling. I'm the Sustainability Manager with the British Construction Steelwork Association. And for the next 45 minutes or so, I'll be speaking to you about fire and steel construction. The agenda for today is that I'll start off talking for a little while about the regulations and prescriptive approaches to fire safety. I'll then spend a little bit of time discussing what fire testing is actually about. I'll spend a fair bit of time discussing types of fire protection and also a little bit on trends in structural fire protection. I'll then talk about something which is becoming increasingly important with the introduction of the new Eurocodes, which is engineering approaches to fire protection. And I'll finish off by talking about engineering approaches to fire safety in general, which is a fairly hot topic at the moment as well. The first thing to say is that fire in big buildings are rare. And today's presentation is really about fire in multi-story buildings. Single-story buildings don't usually require fire protection. There are a number of exceptions to that rule, but in a general sense, single-story buildings do not require fire protection. So today's presentation is going to concentrate on multi-story buildings. And as I say, really big fires in big multi-story buildings are actually relatively rare. I've been using this slide now in front of you for over 20 years, and I make no apologies for it because it remains the best example of a fire in a large multi-story building, a large multi-story steel building that I've come across. It's a building in Churchill Plaza in Basingstoke. The fire started on the 8th floor, completely gutted the 8th floor, spread to the 9th floor, mainly out through the windows and around the side of the building, completely gutted the 9th floor and got to the 10th floor, which had very badly damaged before the fire brigade eventually brought it under control. That fire lasted about 4 hours and caused round about £20 million worth of damage. And if you'd gone into the building afterwards, you'd have seen this site here. Now, ignore the fact that the service ducts have fallen down or are on the point of collapse, and ignore the burnout if you can, and concentrate on the beams and the columns. You'll see there that the beams are fire protected using something called a spray protection material, and you'll get some better image of that material in just a few minutes. The columns are fire protected using a board protection material. And also, if you look up at the top of this image, you'll see that the building is a composite metal deck. That's a composite metal deck structure you see there. At the time this building was constructed in the mid-1980s, that would have been quite a common combination of fire protection materials. Also, at the time this building was constructed, it required 90 minutes fire resistance. So that building survived a 4-hour fire with 90 minutes fire resistance, and it did it without any structural damage. In fact, that building was fully repaired, and after the fire, the floor survived all the reload tests. A couple of years after that fire, the regulations or the rules changed. Now, they didn't change as a result of this fire. They changed for a number of reasons. But when the rule changes came in, that building would have required 120 minutes plus a sprinkler system, which is what it requires now. And that, I think, gives us confidence. The survival of buildings like this in large fire gives us confidence that where we get our fire precautions right, they work very well. And also that there is a lot of conservatism in there as well. By the way, I should have said right at the start as well that please put any questions you have in. There's a facility for putting questions in. Please put any questions in as we go along. Right. If you want to look at the building regulations in this country, and I'm going to mainly be talking about England here, but the building regulations tell us what to do but not how to do it. They're couched in what are called functional terms. These are typical examples of what you find in the big building regulations, and this is what sets out your legal responsibilities as a designer. So, for example, in terms of stability, all the building regulations say is the building should be designed and constructed so that in the event of a fire, its stability will be maintained for a reasonable period. Also, in terms of, for example, lateral spread of fire, the external walls of the building should adequately resist the spread of flames. So that's all it says. So the building regulations tell us what to do, but not how to do it. But the people in government, what they do is they publish approved documents. Many listeners will be familiar with the approved document system in England and Wales. Effectively, the approved documents are mechanisms for meeting the requirements of the building regulations. A lot of people think that the approved documents are the regulations. They are not. They are means, and only one means, by which the requirements of the building regulations can be met. You don't have to use approved documents, but the vast majority of buildings are designed and constructed using approved documents. Approved document B is the one that relates to fire and to fire precautions in buildings. These are downloadable for free off the internet. And if you go into approved document B and you look at recommendations on structural fire resistance, what you'll find is a table A2. Now, I've paraphrased it here. It's actually a little bit more complicated than this in the actual document. But what you'll see in there is that the requirements change depending on the occupancy. So they're different for offices, shops, commercial, assembly, recreation, industrial, etc. They also change with height. So they change at 5 meters, they change at 18 meters, and they change at 30 meters. And that reflects the increased risk as buildings get taller. Now, if I was to go around to people listening to this and ask them to name a multi-story building, I'm guessing that most people would say things like, oh, the Canary Wharf Tower or the NatWest Tower. In fact, the vast majority, the huge majority of multi-story buildings in this country are 2, 3, and 4-story buildings. The tall buildings tend to get the attention, but relatively speaking, they're actually quite rare. Most non-domestic multi-story buildings are offices, shops, and assembly type buildings, and therefore most multi-story buildings fall into the red box there. And what you can see is that the dominant period of fire resistance in England and Wales is 60 minutes. I think by floor area, about 70–75% of buildings require 60 minutes fire resistance. Height is measured in what might appear to be a slightly peculiar way. The height is measured not to the absolute top of the building. It's measured from the ground floor, from the ground to the surface at the top level. The height reflects access height for the fire brigades. So in the previous slide, you'll remember that height change, or fire resistance requirements changed at 5 meters. Buildings less than 5 meters had their own fire resistance requirements. In fact, in the approved document, what this means is that buildings under 5 meters are effectively 2-story buildings. There is now an alternative to the approved document. There are quite a few alternatives. One of the main ones is 9999, BS 9999. This has been around since about 2008. And it is an alternative approach to the approved document. I've got to put my hand up here and say that I have a personal interest in this, because I did have some involvement in the preparation of parts of it. But I think that in many ways it's a superior document to the approved document. There's nothing wrong with the approved document, and it has served us well. But it is a document that, in my opinion, has developed more or less by trial and error over a lot of years, and doesn't perhaps have a huge amount of scientific rigor behind it. BS 9999 is based on an understanding of how risk is created in fire. And if you go in there, one of the things you will find is that quite a lot of the structural fire resistance requirements are lower than they are in approved document B. So, for example, office buildings over 30 meters in height, in 9999, they require 75 minutes fire resistance if they're sprinklered. In approved document B, they would require 120 minutes fire resistance, and they would have to be sprinklered. Also, 2-story office blocks less than 1,000 square meters in plan, in 9999, that can be left unprotected. In approved document B, they would require 30 minutes fire resistance. You might think, hold on a second, there aren't a lot of those types of buildings. There's actually an awful lot of those types of buildings. Just a couple of features of 9999. Like I said, it's based on an understanding of how risk is created in fire. And fire ratings change according to the 4 big risk factors in fire. The 4 huge risk factors in fire: building size, familiarity with the building, whether people are asleep, a degree of mobility of the occupants. And of those four, the big two, really, the biggest one is whether occupants are asleep. Probably the second biggest in terms of importance is familiarity with the building. And that's why the vast majority of people who die in fires actually die in their own houses, and they die when they're asleep, an awful lot of them. And this fact of familiarity of occupants with the building and whether occupants are asleep, as an example, it tells you why hotel fires potentially are so dangerous, and why hotels put so much training into the into fire precautions and the training of their staff as well for what to do in fire. Other factors which affect fire resistance requirements and fire precautions in 9999 are things like fire load, compartment size, presence or otherwise of sprinklers and things like that. 9999 is not all about reducing fire resistance requirements compared to approved document B. There are certain situations where this risk-based assessment has actually identified potential shortcomings in approved document. And one of those is in very tall buildings, buildings over 60 meters. So buildings over 60 meters, in approved in 9999 are actually regarded as special cases and require special precautions in fire. Right, I've talked to you quite a bit about fire resistance periods. I've mentioned 30 minutes, 60 minutes, 120 minutes, and so on. What does it actually mean? Does it mean, for example, that if you have a building with 60 minutes fire resistance and there's a fire in there, that after 60 minutes the building will collapse? It doesn't mean that at all. It means something very, very specific. You're looking there at a photograph of, or an image of what's called a floor furnace. And a floor furnace is used for testing, fire testing, horizontal elements of construction, things like beams and floor slabs and so on. When we talk about something an hour's fire resistance, so let's suppose we're talking about a protected beam having an hour's fire resistance, it's very specific what it means. It means if you put a steel beam into a furnace like that, and test it according to the requirements of the standards. And I've given the details there of three of the main standards that are used: BS 476, ISO 834, BSEN 1361. If you test them according to the requirements of that, it will survive for 1 hour. And similarly, if you test a fire doors and windows and things are tested in different types of furnaces, but they will all have the same criteria as well. They will survive for 1 hour. And it gives you a comfort that all these methods of construction, all these fires, all these pieces of construction, elements of construction with a fire-resistant function will all pretty much give you the same resistance to fire. And it works pretty well. It has worked for quite a lot of years. But if you look at if you want to know more about this, there is a website, steelconstruction.info. Steelconstruction.info is kind of the encyclopedia of the steel industry. Steelconstruction.info/fire_testing will tell you an awful lot more about testing and fire testing. But if you go in there, if you put something into one of these furnaces, the furnace is heated up using what they call a standard fire exposure heating curve, and it follows that pattern there. And there's actually an equation for it, quite a complex little equation, as you can see. Now, there's a couple of things about that. First of all, one of the things you'll see is that it goes up all the time. In practice, in a real fire, the only way that's going to happen is if the fire brigade stand there chucking paraffin on it. I've never seen that happen yet. In reality, what will happen in a real fire is something like what you see in the red curve there. That is probably more like what will happen in a real fire in a real compartment. You'll get a period of growth of the fire, you'll get a period of maturity, and you'll get a period of decay. And what that tells you is that the standard fire test is almost certainly much more severe than any real fire you'll get in practice. It's actually really difficult to get a fire test, a natural fire test, to be as severe as a standard fire test. And I know that because I've tried. It can be done, but it's really quite difficult. And this particular slide, that red line also explains to you why the fire we saw right at the start, the fire in Basingstoke, that fire, to remind you, survived a 4-hour burnout, even though it had only 90 minutes fire resistance. Well, it survived a 4-hour burnout with 90 minutes fire resistance because at any specific place and time, that structure was exposed to a fire, possibly something like you see there in red. In other words, the whole building wasn't exposed to all the full fire severity all the time. The fire traveled, and as it burned stuff out, it traveled and then went away and burned somewhere else. Right, structural fire protection. I'm going to talk a little bit about structural fire protection now. So all these materials here that you're going to see now have all been tested in a standard fire test. Spray protection materials, we don't see a huge amount of them now. They can be made from a variety of different materials. Some products can be used externally as well. Some products have been developed for the petrochemical and the oil industries as well. I don't see a huge amount of this now. It used to be very, very common 20, 25 years ago. It's a bit of a niche product now, I think. I tended to see it in this country mainly in buildings which maybe have an American influence in design, because when you go to America, you see this material all over the place. The one place I have seen it, anybody who's familiar with Canary Wharf, pretty much all the big buildings, the tall buildings at Canary Wharf, are all fire protected using this material. It has a certain very distinct advantages and disadvantages. In terms of advantages, it's a fairly quick action. It is low cost, and the material is actually quite low cost. Most of the cost of this stuff is actually getting the people on site, the people and equipment on site. It's easy to cover complex details. It can potentially, in some cases, be applied to non-prime steel, and as I said, some types may be used externally. The disadvantages, it ain't particularly aesthetic, so you wouldn't use it where appearance is important. It is a wet application on site, and that has impacts on the critical path of the construction process. Probably the biggest problem I find with it, or I have found with it, it needs a lot of shielding. It needs a lot of shielding against overspray, and it can also restrict other trades, which is kind of a critical path issue as well. Board protection materials. Board protection materials are still very common, really quite common. They come in two kind of families. They come in lightweight and heavyweight. Lightweight boards, typically about 150 to 250 kilograms per meter cubed, are used where aesthetics aren't important and where you don't really want to look at it. The heavyweight boards will take renders and decorative finishes, and they are used where aesthetics are important. And what you're looking at there up in the top image is a situation where both of them are used together. It is important you get it right. You would not use a heavyweight decorative board above a suspended ceiling because it costs an awful lot more. There is a big cost differential between the two of them. They are very commonly used. They don't have the majority use in new buildings, as we'll see in a few minutes, but they are very, very extensively used in refurbishment. There's a big refurbishment market in this country, and my understanding is that it tends to be dominated by board protection systems. Advantages and good advantages. If you use a rigid material, heavy, hard material, you can have a good appearance. It's dry fixing. Thicknesses are pretty much guaranteed because it comes in discrete thicknesses. No surface preparation is needed. Some products can be used in limited external applications as well. You'd need to check that to make sure. The costs, especially for the rigid materials, the decorative materials, can be high. It can be slow to fix at times as well. Despite what you saw on the lower image in the previous slide, actually it is difficult to fix around complex details. It's very rarely used with cellular sections, and cellular sections are hugely popular now and hugely attractive. So it tends not to get used with cellular sections because of the difficulties of making the holes. I have actually seen it done, but it's very rare. Another type of fire protection, blanket systems. Personally, I'm a little surprised that these aren't used more often. Flexible blankets. There's actually only one or two suppliers in. They are a relatively low-cost form of fire protection, and they have certain very distinct advantages. Dry fixing, which is always good. Thickness is guaranteed, which is always good. No surface preparation necessarily needed, and they can be fitted around complex shapes. The disadvantages are non-aesthetic, limited to internal environment, and I've said they're relatively rarely used as a disadvantage. The reality of it is they are relatively rarely used, and as I say, it's something of a surprise to me. But the market for structural fire protection is dominated by intumescent coatings, very specifically thin film intumescent coatings, because you can get thick film intumescent coatings. very occasionally used in buildings, but mainly used in the petrochemical industry. So I'm going to talk now about specifically thin film intumescent coatings. These are paint-like materials. You'll very often hear them referred to as intumescent paints. They're paint-like materials that, when heat is applied, will foam up to form a char, and that char is an excellent insulator. And they're very, very widely used. We've got a couple of images here. The top two images are where it has been applied aesthetically, and as you can see, you can get a beautiful finish. The bottom image is on a cellular beam, and the intumescence, I would say that 99% of the cellular beams that I've seen are fire protected using intumescent coatings. So it's very, very widely used on those. So this is very heavily used. And this is what it looks like. If you put it into a furnace and then take it out again, you'll get this wonderful char, which, like I said, is an excellent insulator. Some advantages: it can provide an aesthetic appearance. And when I came into this industry first a lot of years ago, that's mainly what it was used for. These days, it's used much more widely than that. If you're going to use an aesthetic, getting an aesthetic appearance or look for an aesthetic appearance, you will pay extra. You have to be aware of that. It can cover complex details well. It doesn't take up space or add weight, although this issue of taking up space, whatever thickness there is on it, you have to allow about 50 times that thickness around it for the intumescent to actually expand. It doesn't take up weight, it doesn't add weight, it's a fast application. It can, some materials, not all, but some materials can be used in external applications. You've got to be careful. You've got to make sure you get the specification right, the application right. Make sure you do what the intumescent manufacturer tells you to do as well. But these days, I'm seeing guarantees now for external application up to 20 years. Costs can be high. These are the disadvantages. Costs can be high for aesthetic finishes or where the coating gets very thick. You have to be aware of that. It's a wet application on site. Application can be sensitive to adverse weather conditions, and sometimes it's difficult to use for the high fire ratings. Now, having said that, these days, maybe 10 years ago, that would have been particularly true. These days, it's a lot less true. There's a lot of intumescents now which will give you 120 minutes fire resistance. A couple of things about it. I'm going to dwell on intumescent coatings because it is the dominant form of fire protection in new buildings. It can be applied most of the time, almost all the time I've seen it used, it's spray applied. Generally speaking, there's a maximum thickness on one application, a maximum dry, what they call dry film thickness, DFT, of about 1500 microns. And that's important if you hold on to that figure, because it'll come up again later. It can be aesthetic and non-aesthetic, which I've said. It can be applied on-site or off-site, which I've said. Small sections and high periods of fire resistance. Try and avoid that combination if you can. Because you can end up getting very, very high thicknesses, which can be very expensive. Something to be aware of, thicknesses are higher in closed than in open sections, but closed sections have less surface area. So closed sections are tubes, basically. So thicknesses are higher in tubes than in IRH sections, but tubes have less surface area. Couple of points about off-site application. It's not the answer for every job. It is a premium process. It costs more than on-site application. There's a lot of people do it now. This is a real UK success story. It started in this country. It's starting to spread around the world quite a lot now. It has very, very specific advantages. It streamlines construction. It takes fire protection off the critical path. You get improved quality. It reduces weather dependency, and overall, in the round, it can reduce overall costs. Although, like I said, in terms of upfront costs, it is a premium process. It's not the answer for every job. I've tended to see it used in jobs where speed is of the essence, speculative jobs, jobs where access is difficult, those sort of things. I would say that in terms of what I've seen, probably 80% of it goes into construction in the south and southeast of the country as well. But it is quite a big success story. Couple of things about fire protection in general. About 75% of multi-story steelwork in the UK is protected with thin film intumescence. About 30% of that is applied off-site. And as I said, mainly, but not exclusively, used in London and the southeast. Mainly used for non-aesthetic applications. I have seen it used for aesthetic, but it's difficult because some damage is inevitable in transit. And it's difficult to get the damage repair to match the original coating, so you have to be careful of that, but it can be done. Typical costs, my best information, 60 minutes non-aesthetic, probably 16 to 20 pound a square meter. And that includes the shot blasting, priming, and damage repair. There is a model specification. The Association for Specialist Fire Protection, which represents the fire protection manufacturers and applicators, which is an excellent organization, has a code of practice. It's basically a model specification. You can go on the ASFP website and download this for free. It's a really good document. It's there basically to keep the cowboys out. And it's been very successful in that, I think. And it contains clauses which you can actually take out of that document and put into your own contract documents if you wish. So I recommend this. You can use fire protection in combinations. On the top right-hand corner there, that's a board and spray like you saw at Basingstoke. Not particularly common these days, I would say. A more common one on the left-hand side, board and thin film intumescent coating, although this particular one is kind of the wrong way around, because when I tend to see board and spray combinations, I tend to find the board and the column and, sorry, the board and intumescent combinations, I tend to find the board on the column and the intumescent on the beam. Passive fire protection. If you want to know more about passive fire protection, there is an excellent document, again, available from the ASFP. It's known very widely as the Yellow Book for reasons which I think are obvious. Now in its 5th edition, please do have a look at it if you are interested in getting into this area or you want to know more structural fire protection. It contains a wealth of information, and again, it can be downloaded free. You don't have to use passive fire protection. You don't have to use those proprietary systems that I mentioned previously. You can, if you want, actually try and build in the fire resistance into your construction. One of the popular ways of doing that is to use reinforced concrete filled hollow section. And this is, I've started to see this now becoming really quite common. If you go to steelconstruction.info and you look up an article called Hollow Sections in Fire, so that's hollow_sections_in_fire, you will actually find a lot more about this. And you'll also find access to a piece of software called FireSoft, which will enable you to design these reinforced concrete filled hollow columns. So again, if you're interested in it, I would recommend you have a look at that. Probably the other very common way or popular way of achieving inherent fire resistance is to use a method of construction called slim deck. This is an asymmetric beam which actually puts the metal deck, deep metal deck, on the bottom flange and then surrounds the beam with the concrete floor. And you can get up to an hour's fire resistance in that. The great thing about building in fire resistance like that, having inherent fire resistance, is nobody can come and damage it or knock it or anything like that at a later date. And trends in structural fire protection, I already alluded to this. You can see there that over the last 20 years, the story really has been the rise and rise of thin film intumescent coatings. And it shows no real sign of abating. It's up at around 75% now. The next most common is board protection system, although, as I said previously, board does have a big market in refurb. And what we've done in this slide is actually the same slide, but we've separated out off-site and on-site intumescent coatings. So on-site is in the green and off-site is in the red. And you can see there the ratio is probably around 2 or 3 to 1. But between them, they have about 75%. And we're quite fortunate in the country in that we've developed what I call a virtuous circle. As more fire protection manufacturers enter the market, that increases competition, that reduces prices. Steel is more cost effective, more steel is used, more fire protection manufacturers enter the market, and so on you go. And we're looking to have a very efficient fire protection market in this country. Right, I'm going to talk now about engineering approaches to fire protection. When we put fire protection, if we put on an hour's fire protection, let's suppose we put an hour, enough intumescent coating on a beam to provide an hour's fire protection. What does that mean? Well, the default meaning of it in BS 5950 Part 8, which is what we've been using until quite recently, is that for a non-composite beam carrying a concrete floor slab, it will prevent that getting to 620 degrees centigrade. So the limiting temperature for a non-composite beam carrying a concrete floor slab is 620 degrees centigrade. So if you don't know anything else, you will put enough intumescent on that beam to prevent it getting to 620 degrees centigrade in 1 hour. And for a composite beam, it's 580 degrees, and for a column, it's 550 degrees. We're now dealing with the Eurocodes, and the Eurocodes have taken over from 595, I think, in my opinion, with astonishing speed. In the Eurocodes, what we call limiting temperature is called critical temperature. So I'm going to use those terms interchangeably. But what you'll see there is that it's actually a more complex situation. The Eurocode splits up into different types of buildings. And also, if you look at it, you'll see that those figures are generally lower than they were in 5950 Part 8. In other words, you have to prevent the steel reaching a lower critical or limiting temperature. And what that means is that you need to increase the amount of fire protection that you require. So one of the consequences of the move to Eurocodes is that the amount of fire protection we'll be putting on our steel is going to increase. Now, for boards and sprays, that probably isn't going to make a huge difference, but Intumescent is a value engineered product, and a lot of the cost of the material is a lot of the cost of application is in the material itself. So potentially, that's that potential there for to make a bigger difference with Intumescent coatings. And to understand where I'm going to go next, you need to understand how fire protection is specified. Fire protection is specified on the basis of something called the section factor, which is the heated perimeter over the cross-sectional area, very often called the HP/A or the A/V. If you want to know more about it, again, there's an article called Calculating Section Factors on steelconstruction.info. Basically, the lower your HP/A or the lower your section factor, the better. Because a squat, thick beam will have a small heated perimeter in a large area. A thin, narrow beam will have a small cross-sectional area and a big heated perimeter. So the beam on your right will heat up much more quickly than the beam on your left. And the beam on your right will need a lot more fire protection than the beam on your left. Now, you don't need to worry too much about it because there's the HP/A, the section factors, or the A/Vs, as they're called now, are published all over the shop. And the manufacturers publish it, ASFP publish it, Tata Steel publishes. And this is fairly typical of what you would find in the steel construction industry e-blue book. So if you're looking at, for example, 457-19161, a very common beam, and you're looking at a beam of that sort carrying a concrete floor slab, your HP/A, your section factor, your A/V, is 75. It's 75 meters to the -1. That's fairly straightforward. So you've determined that, you've determined the section factor, and then you would go to the manufacturer's information, manufacturer's product information, or you'll find some information on this as well, potentially in the yellow book. So first of all, you have to ensure that you're using the correct limiting or critical temperature. In this case, we're going to look at 620 degrees centigrade. So this is a situation where we would be assuming that we're still using 5950 Part 8. Although, as I said, it's kind of falling out of favor now. So there's your 620 degrees centigrade. And then you want to determine the dry film thickness requirement for the fire resistant period. So your A/V was 75. 75 isn't on that list, but 90 is. And that tells you need 357 microns. For 60 minutes, there you go. Basically, what it is saying is that for this beam, you actually need 357 microns. In fact, you could interpolate between that 357 and that 319 because your actual section factor is 75. And if you do that, you'll find that your required thickness is about 330 microns if you just do a little bit of interpolation. Now, I'm assuming here that most people listening are probably engineers and architects. You will never need to go to this level of detail, probably. Leave this to the manufacturer or the applicator. But for what's going to happen now, it is important that you know that this process is there. So a couple of things to note. Like I said, I'm going to repeat what I said previously. The reduced critical temperatures in the Eurocode mean that fire protection thicknesses are going to increase. That's going to happen. One thing to note is many structural sections are not fully utilized. A lot of beams, for example, are designed not for load carrying capacity. They're designed for vibration or deflection. Or you'll find that the fabricator comes along and he has 10 different types of beam on his floor, and what he'll do is he'll rationalize. He'll say, right, other than me fabricating 10 different types of beams, I'll fabricate 2 different types of beams and put in some heavy beams. So there's a lot of structural redundancy in an awful lot of beams and columns. And this can be used to increase critical temperatures, and we'll see that in a minute. The bigger the section factor and the higher the period of fire resistance, the more value this approach of increasing critical temperature, designing to increase critical temperature, is going to have. As I said previously, it's more likely to have greater value when dealing with intumescents and sprays and boards, although potentially it could have value for sprays and boards. We're going to look at it in terms of intumescents. And like I said, this is because with intumescents, a higher proportion applied cost in the materials. So let's have an example. Let's consider a 254 UKC 73, a bog standard column that you'll see in loads of buildings. All the calculations here are going to be based on a product called Interchar 2090, which comes from International Paints. So, so it's a solvent-based material which can be used on-site or off-site. The maximum dry film thickness that can be applied in one pass is 1500 microns. You'll see the importance of that in just a minute. All thicknesses of this product will have been certified in accordance with testing to BS 476. We're looking at potentially office loading, and we're looking at I say office loading because the variable load factor in fire changes according to the occupancy. Structural calculations are in accordance with 1993 part 1.2, and we're looking at a couple of assumptions here. A 50-50 split of permanent and variable loads, what we used to call the old dead and live load. Column height 3.5 meters. The steel grade is 355 newtons per millimeter squared, which is now the standard steel grade. The column is within a brace frame and located at an intermediate story. I won't go into the details of why that last point is important. It's just to say that the fire parts of the Eurocode allow you to take effective lengths, and they value the effective length factor a function of whether the column is on an intermediate story or an upper story. But I won't go into the details of that. So dry film thicknesses. The default critical temperature for hot roll steel sections compression in office is 563 degrees centigrade. You saw that a few minutes ago. I don't expect you to have taken it in, but just believe me for the moment that it is. From information supplied by International Paints, the DFT required to achieve 90 minutes fire resistance is 1812 microns. To achieve 120 minutes, 3064. This will require 2 and 3 coats of intumescent respectively. And just to show you the difference that makes, a 254 UKC 73 has a heated perimeter of approximately 1.5 meters. A 3.5 meter length therefore has a surface area of 5.2 meters squared. Therefore, to apply a coating to give 90 minutes fire resistance, the applicator will have to coat 10.5 meters squared. And to give 120 minutes fire resistance, he or she will have to coat 15.75 meters squared. And that is how an applicator thinks of it, and that is how an applicator costs it. So if you can get those coating thicknesses down, that would be fantastic. So we had a look at that, and we had a look at what would happen if the beams were, or the column was not fully utilized. The first thing to say was that the 563 degrees centigrade we showed in the previous slide assumed was a default. But in fact, that's the worst case scenario for columns. In fact, for that particular column, the critical temperature was 591 degrees centigrade. And that immediately brought the 90-minute dry film thickness down to 1394. So just doing that and nothing else brought that from a 2-coat system down to a 1-coat system. And that would have a huge impact on the economics. If we assume the utilization of 0.8, which would probably be very reasonable in a lot of situations, the critical temperature goes to 629, the dry film thickness goes to 1100, and suddenly you're talking about very significant savings indeed. 0.6, 0.4, 0.2, you're probably not going to get to those sort of utilization ratios for a column in practice, but it's interesting to see the difference that they make. And what you're looking at there is figures in green are 1-pass application, and figures in red are 2-pass application. And just what we've done there will have an immense impact on the economics of fire protecting that particular column. If we look at it in another way, there's something else you can do as well. You can actually change the beam size. So if we go to the default, we're looking at the 254 UK73. We say the default situation in this case is it has an 80% utilization, which is probably realistic. Critical temperature 629, 90 minutes DFT 1100, which is precisely what we had in the previous slide. If we actually went to a bigger column, we would actually end up doing something interesting. We'd reduce the section factor and we would reduce the utilization. And suddenly you're down to 843. If we column again, you're down to 672, and there you go. Now, in practice, you could look at that, and my personal opinion is you probably would not go to the bigger columns in that instance. The reduction in the thickness probably is not sufficient to offset the increased cost of the steel. But there will be situations where it will be, especially where you'll end up going from 3 passes to 2 passes, or 2 passes down to 1 pass. So that basically is, in fairly simple form, the how you kind of engineer fire protection materials, in particular intumescent coatings. I haven't gone into any huge detail in it. I've just given you an overview, but at least you now know what is possible. Right, I'm going to finish off today's presentation by talking about engineered approaches to fire safety in general. I'm going to go back to approved document B. Approved document B has an interesting statement at the front. There's no obligation to adopt any particular solution. I intimated that at the start. Fire safety engineering can provide an alternative approach to fire safety. And the really interesting bit, it may be the only viable way to a satisfactory standard of fire safety in some large and complex buildings. So basically, what approved document B is saying, actually, hold on a second. In some cases, you should actually look to alternative solutions. And I'm going to go through a couple of examples of what might be considered alternative solutions. The document, the technical standards in Scotland, by the way, have pretty much exactly the same statement. And the example I've got here is from Scotland. It's the Maxim Office Park outside Glasgow. This dates from about 4 or 5 years ago. The work was done by a company called Jeremy Gardner Associates. Now, in this particular instance, what Jeremy Gardner Associates did was, in terms of fire engineering, was they did what is possibly the simplest and most basic form of fire engineering. They calculated something called time equivalence. What time equivalent is, the basis of it, is a calculation which calculates how severe your fire is compared to a standard fire. So if you did a time equivalent in the office that you're sitting in, and the answer was 30 minutes, it means that a fire in that office would be as severe as a standard fire for 30 minutes. So that's what it actually means. This particular build complex, there was 10 buildings, each building designed as a simple compartment, a single compartment of more than 4,000 square meters. According to the Scottish Technical Handbook, that required 120 minutes fire resistance. When the engineer looked at the time equivalent calculations, taking into account ventilation conditions, fire load, and surface linings, they're the 3 things which tend to dictate how severe a fire is in a real building. He worked out a time equivalent of somewhere between 26 to 28 minutes. So the next thing he did was he then looked at a sensitivity analysis. He said, right, we've done things like assume all the windows will break. In fact, if only some of the windows break, you'll actually get a much more severe situation. So let's assume only some windows break. Let's assume somebody stacks up a load of fire in that fire load in that building is used as a storage area, things like that. So they looked at sensitivity analysis as well. And when they did that, what they put forward to the authorities and what was accepted was that the fire resistance in 9 buildings was 60 minutes, and in one building it was 90 minutes. And that approach is a fairly standard approach in large buildings requiring high periods of fire resistance. If you want to look at another example, this example is a very good one from Arab Fire. I was at a presentation a few years ago where they showed this, and it is a care home. And if you look there at those kind of thick red lines, that is the compartmentation in there. And they separated up the care home, and according to approved document B, they've now done everything that they need to do. That's it, in the story. But in fact, an engineered approach immediately shows a problem, and you can probably see it straight away, which is that a fire in one compartment could potentially break across the courtyard and into the other compartment. An engineered approach actually said, yeah, that can happen. So let's come along and let's put in mainly some integrity glass in there to prevent the fire spread across that courtyard. Now that is, you can sit and think, hold on a second, that's very simple, that's very straightforward. It is, but a lot of the engineering approach is common sense, just using common sense, not allowing yourself to stick rigidly to prescribed rules. And that's what they did. In terms of structural fire engineering, I'm going to move on to a little bit about structural fire engineering for 5 minutes now. Structural fire engineering is supported by the Institution of Structural Engineers, and they have a publication on it. It dates from 2007, so it's moving on a bit, but it's still very relevant. And they support the use of engineered solutions. And in terms of engineered solutions for structural engineering solutions, most of what we do now dates back to a series of fire tests which were carried out at a place called Carrington in the mid and late 1990s, in the mid and late 1990s. The building in question was a bog standard 5 bay by 3 bay, 8-story composite metal deck building. And there was a series of fire tests carried out in that, which were probably as severe as anything which will ever be undertaken anywhere. And these fire tests, then, the results of these fire tests underpinned the development of very advanced, sophisticated structural fire engineering methods. And we're very fortunate in this country that we have some of the very top fire engineering consultants in the world in this country who can take advantage of that. I won't go into the details of how it was, how this was done and how this is done, how this process is done, but how this process is done. But if you look at the results, a typical result would be this. This is some work that was done by Arup again, and this is Plantation Place South. And this was one of the first buildings which use this advanced engineering process. And as you can see, they've taken a lot of the cost out of that building because they can leave secondary beams unprotected. They can demonstrate that you can leave secondary beams unprotected, although there may be some compensating features that may be required as well. So this is now becoming very much a standard method of fire protection and our fire engineering. And this process was probably shown most recently. A very good example was the spire. This comes from WSP Fire, who did the work on this. And if you look at the floor plates on the spire, anything that's in there in red is fire protected. Anything which is not highlighted in red is unprotected. And as I say, for large buildings, complex buildings, composite metal deck, I'll repeat again, this process, this methodology applies to composite metal deck buildings, because only in composite metal deck buildings do you get the robustness and the continuity that allows you to leave the secondary beams unprotected. But this is now becoming a standard process for buildings like that. And I will finish at that. There's lots more information on steelconstruction.info. Go to structural_fire_engineering if you want to know more a bit more about that last subject. And that's it. Thank you very much.